So in the last video we saw how paging works, right? I know it is a little bit difficult to understand. So what I did is I'm going to take one more example for explaining paging. Okay, the same problem which we saw, actually I have changed the numbers and I'm going to explain it. Okay, how it works. Fine. They are given that logical address space equal to 16 MB. Okay, and physical address space is 16 GB. See, what is meant by logical address space? It is nothing but the size of the process. Okay, and physical address space means size of the RAM. And also they have given that page size is 128 KB. Okay, single size of single C. In case if page size equal to 128 KB, then obviously frame size will also be 128 KB. Okay, fine. Now they have also given that it is a byte addressable system, which means for every byte we associate an address. Fine. Now from this we can calculate the number of frames and number of pages, right? They have given logical address space, physical address space and page size. From this we can calculate the number of frames and number of pages. Number of frames is nothing but physical address space divided by frame size, right? Physical address space is nothing but 16 GB. See, these things I can convert in terms of 2 power, right? For example, 16 MB is nothing but 2 power 4 into 2 power 20 bytes, right? 2 power 4 into 2 power 20 is 2 power 24. So it is nothing but 2 power 24 bytes. Similarly, this is 2 power 4 into 2 power 30 bytes, right? 2 power 4 into 2 power 30 is nothing but 2 power 34. So it is 2 power 34 bytes. Similarly, this is 2 power 7, this is 2 power 10. 2 power 7 into 2 power 10 is 2 power 17, okay? So this is 2 power 17 bytes. Fine. Now let's see this. Physical address space is nothing but 2 power 34 bytes and frame size is nothing but 2 power 17 bytes. So 2 power 34 divided by 2 power 17 is nothing but 2 power 17. See, bytes and bytes are getting cancelled, right? So it is nothing but 2 power 17 frames will be present inside our RAM. Okay. See, what if you want you can check it. 2 power 17 frames with each frame having 2 power 17 bytes. So 2 power 17 into 2 power 17 is nothing but 2 power 34, right? And we got the answer 2 power 34 bytes, right? This is the total size of the RAM. Fine. Now let's compute the number of pages. Number of pages is nothing but logical address space divided by page size. And logical address space is given as 2 power 24 bytes. Fine. Page size is given as 2 power 17 bytes. Fine. 2 power 24 divided by 2 power 17 is nothing but 2 power 7, right? Bytes and bytes will get cancelled and so it is 2 power 7 pages. So how frames will see how a RAM will look like is, let us assume this is our RAM. Okay, it will have a lot of frames. Fine. I'm starting with 0, 1, 2 and so on. It will keep on going till, see, we have a total of 2 power 17 frames, right? 2 power 17 frames. So in case if I start counting from 1, it could have ended at 2 power 17. But since I'm starting at 0, we will always start with 0. It will come till 2 power 17 minus 1. Okay. In case if you want, you can calculate it. It is 2 power 17 minus 1. Fine. This is how RAM is looking like. Okay. This is how RAM is looking like. Now how our process will look like? Our process is nothing, our process logical address space or process, okay, anything is fine. Now logical address space has actually 2 power 7 pages, right? So it will start with 0, 1 and so on. It will keep on going till 2 power 7 minus 1. Okay, since we are starting to count from 0, it will go till 2 power 7 minus 1. Now one thing you need to understand from this is, see, though I have mentioned it as 0, 1, 2 and so on up to 2 power 17 minus 1, all these addresses will be in binary, right? All these addresses will be in binary. Now in how many bits will those things be represented? That is very important, right? That really depends on how many frames we have. See, all these are frame numbers, right? They are not addresses. This is 0th frame, this is first frame, second frame, and so on up to 2 power 17 minus 1. All these numbers will be in binary, and number of bits for this addresses really depends on the number of frames. Here, since we have 2 power 17 frames, we need 17 bits in order to represent the physical address. Okay, in order to represent the frame number. Okay, here since we have 2 power 17 frames, see, in case if we have 2 power 17 frames, we need 17 bits to indicate the frame number, right? So our frame number field, see, let us assume this is our physical address. Okay, what our physical address will have? Our physical address will have two fields, right? One thing is nothing but frame number, another thing is nothing but frame offset, right? This is how our physical address will look like. Similarly, how our logical address will look like? Our logical address will have, one thing is it will have page number, fine, and it will also have something called as page offset. Now we have calculated that frame number is nothing but 17 bits. Okay, so this is 17 bits, fine. Now how many bits this frame offset field will have? That really depends on how many bytes a single frame is actually having. Okay, how many bytes a single frame has. They have given that page size equal to 2 power 17 bytes, right? Now in order to indicate 2 power 17 bytes, we need 17 bits, right? And so frame offset field will have 17 bits. Also, our page offset field will also have 17 bits. Why? Because we know that frame size equal to page size always. Okay, so I'm writing this as 17 bits. And what will be the page number? How many bits will page number field will have? That really depends on how many pages we have, right? We have 2 power 7 pages. Starting from 0, we are going till 2 power 7 minus 1. So we have a total of 2 power 7 pages. Now in order to indicate 2 power 7 pages, we need 7 bits. Right? Now in case if you add both of them, 17 plus 17 is 34, right? The total physical address size is 34 bits. And so our physical address space is supposed to have 2 power 34 bytes, right? We have a total of 34 bits, fine. And so with 34 bits, we can form 2 power 34 addresses, right? We can form 2 power 34 addresses. And that's the reason we got this physical address space as 2 power 34 bytes. Okay, because every byte is given an address. Similarly, we have a 7 bits over here and 17 bits over here. We have a total of 24 bits, and so the total size of our process, which means logical address space, should be 2 power 24 bytes, and that is how we got here 2 power 24 bytes. Okay, you can verify it in case if you want. Fine. So this is our physical address. Fine. This is our physical address, and this is our logical address. Okay. Now let's see how our CPU will actually execute this process. Okay, that really depends on how the pages of this process are placed in the frame of our RAM, right? Are placed in the frames of our RAM. Fine, but that doesn't matter here. Okay, I'm not actually going to take that, which means I'm not going to take this page and then place it in this frame like that. It can be placed in any arbitrary frame, right? Any page can go into any frame. That doesn't matter. But now what I want to tell you is how our CPU will actually execute this process. Okay, I want to tell you how CPU will actually execute this process. See, our CPU will have something called as our CPU will initially generate the logical address, right? It will generate the logical address. Now, how many bits will our logical address have? It will have 24 bits, okay? So, it will generate this 24-bit logical address. Fine. Now after generating this address, it will understand that, let me rename this process as P1. After generating this logical address, it will understand that, okay, in order to execute this byte, I need to get the page table of process P1, right? It needs to understand that. After understanding that, what it will do is it will load the page table base address, okay, of process P1. Page table base address of process P1. once it is loaded, it will be able to get into the page table of process P1. Okay, the page table of process P1 will have exactly 2 power 7 entries, right? It will exactly have 0, 1 and so on up to 2 power 7 minus 1. It will have 2 power 7 entries. Why? Because here we have 2 power 7 pages, and for every page we will have an entry in the page table. We know that, right? And so we will exactly have 2 power 7 entries. Now, in our logical address, here is what our logical address is present, right? Our CPU has generated logical address. Now our logical address will look like this. Now in this logical address, this 7 bits is actually indicating the page number, right? Now whatever this is indicating, we will go to that entry number, right? This 7-bit page number field is what is being used by our CPU in order to select the entry number in the page table. Okay, in order to select the entry number in the page table. In case if it is 5, which means they have indicated that page number is 5, they will go into the entry number 5 in this page table. Using that, they will understand the frame number in which the byte which we are searching for, which means the byte which is being indicated by logical address is present. Okay, see, we need to find out the exact frame in which this byte is actually present. Okay, for that reason we will get into the page table by using the page number field, and then we will find out the frame number. Once the frame number is found out, what we will do is we will replace the 7 bits, which means we will replace the 7 bits using the 17 bits. Okay, see, so far we have not calculated the physical address. I have just shown it before. Now CPU has generated the logical address, then it actually went to the page table, then it found out the frame number, then it replaced the page number with frame number. And in case if it replaces this page number with frame number, we have actually converted this logical address into physical address, right? Now our CPU has got the physical address. Now it is very easy for CPU to actually fetch that byte. Okay, why CPU is fetching that byte? Because it needs to place in register and need to execute, right? Fine. Now how will it actually find out? Using the 17 bits, it will actually find out the frame number. For example, in case if it is 2, using the 17 bits, in case if I have the number 2, how it will be indicated? It will have 0, 0, 0 and so on. It will end with 1, 0, right? This is how 2 will be indicated using 17 bits. Now using this, it will go to the frame number 2. Fine. Now using the 17 bits, we will have the byte number, right? We will have a total of 2 power 17 minus 1 bytes in a single frame, right? That is what they have indicated. Page size is equal to 2 power 17 bytes. And so we will have a total of 2 power 17 bytes over here. Now among this 2 power 17 bytes, which byte I need to choose really depends on this offset. Okay, frame offset. Using the 17 bits, I will actually pick the correct byte, and that will be given to the CPU. Now CPU will happily execute it. Okay, so this is how paging actually works. Fine. See, this page table, this is actually helping the CPU in order to reach the exact byte, right? In case if we don't have this page table, see, because of this page table, we are able to find out the frame number and we are able to reach the process. And so we say this page table as memory management unit. Okay, this page table, which is actually not just this page table, anything which is helping the CPU in order to get the exact byte in order to execute, we say that as memory management unit. And so we say this page table as memory management unit because it is actually helpful in order to convert the logical address into physical address so that the appropriate byte can be fetched and executed. Okay, I know this video is again a bit more longer, but I think right now you should have got the point. Okay, how paging exactly works. Fine.